Physics 100. For those in my class, I'm your instructor for the semester, Dr. Rhodes. You probably met me in the first class. For those who are just randomly wandering YouTube, I'm Dr. Rhodes, astronomer of IUPUI, teaching Physics 100. This is an algebra-based physics class. If you're in a trig-based physics class, these lecture series will probably help you, but you'll need to do a little bit more advanced work to be able to succeed in your class. It is my goal in these following lectures to teach you everything you need to know to be able to succeed in a algebra-based class, particularly Physics 100. Now, for those who either missed the first day or, again, join us on YouTube, the most important thing I can teach you is how to solve a physics problem. And there is a 4-step process to solving a physics problem. Now, when most students encounter a physics problem, their instinct is to try to grab the appropriate equation and solve. Sounds pretty straightforward. However, it turns out when you do that, you skipped a few steps. I like to call this the physics game, trying to solve a physics problem without thinking about the physics behind the problem. And that's actually a big mistake. That's something you're going to have to try your best to not do. I know it's really hard, because it takes a little bit of extra thought and effort, but try to spend a few extra seconds at the beginning of the problem trying to think out the problem, think through the problem before your pen ever touches the paper. The first step that you need to do in order to solve a physics problem is to first understand what is actually happening from a physics standpoint in the problem. Now, when I say this, this doesn't mean read the problem and just blindly repeat what was written in the problem. This means you have to understand what's actually happening from a physics standpoint in the problem. So a ball flies through the air. You have forces, you have motions. The ball is going to do an arc. These are things you need to know to be able to solve that particular problem. Once you understand what's going on in the problem, sometimes that's enough to solve the problem. But oftentimes now we're going to have to do a calculation. The second thing is going to be to understand what type of problem is this. Now, what type of problem doesn't mean, well, there's a car in the problem, it must be a car problem. I'm throwing a ball through the air, it's a ball problem. Those are not problem types in physics. There are 4 main problem types that we're going to learn about in this class. The first one is motion problems that we're going to focus on today. We're going to learn about force problems, which we did a little bit with in the lecture I gave before I started video recording, which I'll recap very briefly. And we're going to do a lot of the next lecture. Energy problems and momentum problems. And each problem is going to have its own set of rules, its own set of equations, if you will, just like different sports have their different sets of rules. So motion could be football, and force could be baseball, and energy could be basketball, momentum could be, I don't know, badminton. Now you're probably thinking badminton's not a sport. Well, anyone who plays badminton would disagree with you. I'm not one of them, so maybe I should have picked bowling instead, which I don't play either. So those 2 parts are actually the physics part of the physics problem. That is the physics. And understanding what's going on in the problem and what type of problem it is really the understanding for physics that I'm going to have to try to teach you through this series of lectures and through the course. Being able to identify the problem type and to be able to understand what's going on in the problem, that's the physics. The equations are just the tools you're going to use to solve those physics problems once you have an understanding of the problem itself. Kind of like if you're going to build a bookcase, you don't use, you're going to use probably a saw and nails and screws at some point to help you, but saws and nails and screws don't solve the problem. They just are tools to help you solve the problem. And so the next 2 parts are the math part of the physics problem. First, you're going to grab the equations, or equation. A lot of times we'll do, for level 1 and level 2 problems, there'll just be 1 equation. For level 3 problems, there'll usually be 2, maybe 3 equations you'll have to use to solve. And then once you grab the equations, now you do what I like to call the iPod, plug and play. You're going to plug the numbers into the equation and solve for the unknowns, thus solving the problem. Although sometimes in some problems you don't even need to use these 2 steps. The first step will solve it for you. the concept will solve it for you. And in some ways, those are the hardest problems for students to do in this class, even though they're not the hardest problems, as strange as that sounds. So that is the four-step process to solving a physics problem. And if you ask me a question in class, how do I solve this problem? The first thing I'm going to ask you is usually going to be, what is happening in this problem? In other words, I will have you go through the steps. And if you find you can't solve a problem, it's usually because you started at step 3 and you needed to start at step 1. So make sure you're always starting at step 1, because the habits you build now are going to be very helpful for this class. It's really hard to change bad habits later. You want those good physics habits. It'll make the class a lot more straightforward. Now, in this class, we're going to encounter 3 levels of problems, kind of like levels of a video game. Level 1 problems are just questions where, for example, this equation here, I have written d equals vt. I give you the velocity, I give you the time, and I have you calculate the distance. It's pretty straightforward. You don't even have to understand the physics or the equation, you just have to blindly plug the numbers into the equation, and you get your answer. Those are level 1 problems. Now, in real life, in your future careers, you're probably not going to encounter a whole lot of level 1 problems. And if you do, they're going to be kind of pointless because your cell phone could probably solve them for you. So you don't really need to be able to do those problems. I know that sounds strange to say, but if you can't, of course, if you can't do those problems, you can't do the more advanced ones. But those aren't the problems you're going to see a lot on the exams and the homeworks. Those are going to be higher level problems. You'll get a few. I got to throw some straightforward ones at you. But this will not be the focus of the course. And I know a lot of students want to focus on that. But that is not the focus. If all you can do is this, you will not pass this class. This is the next level, level 2. Level 2 requires some thought. Not a lot, but some. In this class, you're going to have to use your brain a lot. Level 2, either going to have to use a complex equation, which means we're going to be something after we add in this thing in the box here, and solve for something. Or you're going to have to start off with the concept and use the concept to help you solve a problem. For example, we might have an object that is moving at a constant velocity. And then I ask you, what is the air resistance force on this object that's falling through the air at a constant velocity? Well, for this problem, if you try to grab the equation first, F equals ma, you're probably not going to get it right. Because the first thing you need is a concept. In this case, the concept, which we covered the first day, and I'll cover again after I go through all this, is that when you have a constant motion, the net force is 0. So then you set 0 equal to the sum of all forces and solve for the air resistance force. So that is a level 2 problem. Not a dreadfully complex equation, but it needs a concept to be able to solve it. And this is more towards the real physics step. Because in your real life, the physics questions are going to come at you, and they're not going to necessarily give you all the values. You're going to have to try to infer things from context. A lot of physics is done through context. It's kind of like driving. You have rules of driving, but when you actually drive, everything is through context. You're driving on, you have one lane, you have to stay in that lane, unless the guy in front of you is stopped and has his blinking lights on, then you know you have to try to go around, you got to make sure the oncoming traffic's not hitting you, etc., etc., etc. That would be kind of like a level 2 driving problem. A level 1 driving problem is you stop at a stop sign and go, and there's no one on the road. Now we go to the level 3. This is where the real physics is. This is the part of the class where I expect the A students to be able to do it. If you want to get an A in the class, you need to be able to do the level 3 problems. You can probably get a B if you do the level 2s. If you can only do the level 1s, then not so much. You may or may not pass the class. But the level 3 problem is where I'm going to try to push you at. Now, in these lectures, we're mostly going to have level 1 and level 2 example problems, because I have to build up your base first before I can throw the level 3s at you. The level 3s will come in recitation and in homework. Even if you're on YouTube in a class at another university, those will mostly come on the recitations, on the homeworks, and of course on the exams. A lot of problems on exams are level 3 problems. Now, what is a level 3 problem? A level 3 problem is either is usually having to apply a concept to a problem and having to use some sort of complex equation to be able to solve the problem. So an example of this is, we're going to see this in momentum later. I give you some of the initial values. You have to use that to figure out the final value for momentum, and then use that momentum to solve for our final velocity for some particular object. Don't worry, that'll be more straightforward later when we cover momentum in about 4 or 5 lectures. So that is my expectations for you in the class. In order to be able to get an A or B or other. All right, so at this point, I'm going to go ahead and start the lecture part. Now, all the lectures are available online. Even if you're not at IUPUI, you can still get to the website. This is the website up here up top, www.physics.iupui.edu/astronomy with a capital A, in this case this is /Rhodes, that's my last name, RHOADS with a capital R, Astro with a capital A, /P100, capital P, /resources.htm. As I bring you to this page, all of these links will be links to the particular PowerPoint presentations. You may want to click on Lecture 2 Inertia if you missed the first day of class, or if you're joining us from YouTube, as I gave that lecture the first day of class. First day of class, obviously I don't expect anyone to have seen things on YouTube, so thus I did it in the class. Now to recap inertia, inertia is Isaac Newton's first law of motion. It states that any object in motion stays in motion unless a force acts upon it. Force is something that pushes or pulls. And an object at rest stays at rest unless an outside force is applied to it. In other words, a rest is a motion of 0. So any motion you have, even a motion of 0, stays in that motion unless you have a force. Now also note that the reverse also applies, that if you have a constant motion, that means you have no net force. And also this applies in each dimension. So if I have a problem where I'm moving horizontally and vertically, so I throw a ball through the air, I will have motions horizontally and motions vertically. Those are completely separate, and they'll have their completely separate forces. So I throw a ball through the air. Usually, if I ignore air resistance, the horizontal force is 0, so the motion of the horizontal will be constant, but you'll have this vertical motion because of gravity. All right, so I think that recaps the first lecture. So now let's go on to the next lecture, which is our first video lecture, which is lecture 1 I don't give. Linear motions. So our goal for this lecture is to understand linear motions. Our objective is to achieve this goal. We're understanding relationships between distance and velocity, between velocity and acceleration, and between distance and acceleration. So let's compare distance to velocity. Some of you may have had physics in high school, you kind of remember the equation. But even if you haven't, let's see if we can figure this out from what we already know. So we have a person, 2 people. They're in their car, they're driving down the freeway. One drives a constant velocity of 50 miles per hour west. In other words, they have the cruise control on, and they encounter no traffic. The second person speeds up and slows down, but their average velocity is 50 miles per hour. How far do they travel? Now, at this point, I suggest you pause the video so that you can do the calculation, although this one you probably do without a calculator, and then restart it when you're finished. I highly encourage people to do the sample problems before you watch me do it, because watching me do problems does not help you solve physics problems, does not teach you the physics. We learn by doing, and that's why I have the sample problems embedded in the lecture itself. So go ahead and do that pause, or calculate now while I erase part of the board, or erase the math part of the board, and we can solve this problem. So the equation that we're going to use here is d equals vt. Now what does that mean? I will write abbreviations on the board a lot of times. D represents distance. V represents velocity, which is your rate at which you change your position times time. Now notice I wrote plus a box because there's something that goes into this box that we don't have for this problem. That it's 0 for this problem. But please keep in mind that there is that box. There is actually no equation d equals vt. Strange as that sounds. I know you're probably thinking at this point, but in high school physics we learned d equals vt. We used it a lot, d equals vt. Well, the problem is that d equals vt is actually a solution to a very small set of problems and not an actual universal equation. And so I try to focus on just a few equations. Now, we're always going to be able to use the full equation that I give to you in just a moment, even when we have a straightforward case like this. It's just that what goes in the box will become 0. So I highly encourage people to not use just d equals vt, because there's only a very specific case when you can use d equals vt, namely when you have no acceleration. But most people forget that. So keep in mind there's a bigger equation there, but we're only using part of it for now. So we're going to use d equals vt because the box equals 0. In fact, I will write plus 0. And I always like to write units. That's one way I differ from other physics teachers. I consider units as part of the problem and direction as well. So you'll see me harp on units and direction all semester long. So here's my equation. Now, what velocity do we use here? Well, there's only two types of velocity we can use there. An average velocity, which we have in part A, or part B, or a constant velocity, which we have in part A. If you don't have a constant or an average, you can't use that equation because what goes in for V is actually going to be slightly different. We actually use what's called the initial velocity, which is a different type of velocity than average or constant. So there's three types of velocities: average velocities, constant velocities, and instantaneous velocities. Instantaneous includes final velocity, initial velocity, or any velocity at any given time and point. Those are instantaneous velocities. You cannot use an instantaneous velocity for d equals vt. You have to use the full equation. That's why it's a little bit tricky there. So, but here we have average and constant, so we just do 50 miles per hour. Now in this class we're usually going to use meters per second, but here I used a term you're going to be more familiar with, unless you're from outside the US. Then this would be about 22 meters per second west. Now notice I put in the west here. For distances you don't have to have directions, but it will help later on, particularly when we're doing this equation here. Plus the zeros. Times time plus 0, and that gives us 200 miles, which you probably solved quite a while ago, but that's how it's done. Now this is, of course, a level 1 problem. Level 1 problem. So you're thinking, well, that's pretty straightforward. Physics is easy. Well, this is only a level 1 problem. Kind of like the video game when they start you off and they're trying to figure out how to push the buttons. So that is distance and velocity. I do quickly want to cover unit conversions because I really don't have much other chance to do it, because you will convert units a lot in physics, more so if you're not in my class. I don't do a whole lot in my class, but a lot of other classes do. So to do a unit conversion, now there's the math way to do this, which is god-awful, and there is the reasoning way to do this. Now the math, if you ask the math department how to do a unit conversion, they will tell you to set up an equation with two fractions, and then you will cross multiply, and you will get it wrong 75% of the time, I kid you not. The best way to do it, your value that's being converted equals the number that you have, the value you have, times a conversion fraction. Now the only thing that it has to watch out for is in this fraction, the top and bottom have to be equal to each other. Or equal to each other. We can do clever conversions which either convert to different types of units or to scale units. So, and this is the value wanted, and this is the value you have. And then you put the number in front based on how many of these equal how many of those. So an example here, if I wanted to convert my time to miles, I have 4 hours, and I know that in this case, 1 hour, and always write in the units, because if you write these in backwards, you'll spot it with the units. I go 50 miles. So I can say that 50 miles equals 1 hour. They don't, but in this problem they kind of do. So then I would do this, and I would get 200 miles. Now, in this problem it's easy to use the equation, but if you're converting, say, millimeters or centimeters to meters or to kilometers or kilograms to grams or vice versa, you'll have to use an equation that looks like this. So if I had 12 kilograms and I was converting to grams, then 1,000 grams equals 1 kilogram, and I have 12,000 grams. So that's how you do unit conversions. It's the same way every time, and it's pretty straightforward this way. It's one step. Otherwise, if you use the math department way, it's about 3 or 4 steps, and they're very complicated steps too. All right, so that is unit conversions in a nutshell. All right, so let's do this now in 2 dimensions. Now, in 2 dimensions, it's the same as 1 dimension, except for we now have 2 separate problems. In this case, we're going to have the north problem and the west problem. When they're perpendicular 90 degrees from each other, they're completely separate. My motion to the north and my motion to the west do not affect each other directly. So what you want to do is draw a line down the center of the paper. And make this the north side, and make this the west side. And here, only things that are north can go here. And here, only things that are west can go here. And so, this requires a bit of a leap because it's very easy to just take the numbers on the piece of paper and just throw them into the equation. And so, if you do that, though, you're going to get the problem completely and utterly wrong. Now, I'm going to have to make a slight change to what I have written here because what I have written here is actually for a trig-based class. So those of you in a trig-based class, this is the kind of question you will see. In the algebra-based class, you have to be given all the values in the different directions, or the left is unknowns for you to solve. So in this case, we have a plane headed west with a velocity 200 miles per hour. So I'm going to put that in the west box. Now we have wind, and the wind acts like a conveyor belt. So here's sort of a concept a little bit. And it's going to carry the plane with it. So 200 miles per hour is the plane's motion with respect to the air. But the air is moving, and so that's going to change the overall velocity of the plane with respect to the ground. Now, in this class, we'll always use what we call relative velocities. Velocities relative to something else. And we have to, because you can't have your actual velocity. We don't know what that is. We are moving 600 kilometers per second towards the Virgo cluster. And I'm pretty sure you're not going to include that in every single problem that you do. So we're going to use relative velocities. And so we want to know, relative to the ground, how far are we going to travel. So we have to calculate what that velocity is. So it's going to be the motion through the air plus the motion of the air. Now the air itself is moving 70 miles per hour in an angle 30 degrees north of west. So it's mostly to the west, but a slight bit to the north. Now, for those of you who know your trig, you'll be able to break down this triangle pretty quickly and know that the north velocity is going to be 35, and that the west velocity is going to be 0.86 times 70, let's call it 60. Now, I do also need to include direction, because if one of these was east, I would have to turn it into a negative west. And this is north. Now, in this class, if this was an exam, I would actually break that number down to you. I would say it's 30 degrees northwest, such that it is traveling 60 miles per hour west and 35 miles per hour north. And those are the numbers you have to plug into the north and west components. So this is going to give us a total velocity of 260 miles per hour west and a make velocity of 35 miles per hour north. Now this becomes a little too problem because we had to do a couple steps. It wasn't just one step, throwing numbers, solve. So this was a level 2 problem. But now we actually solved. And notice I haven't even begun to solve the problem yet. All I've done is figured out what's happening in the problem. I just did step 1. All that was step 1. Now we ask how far will the plane travel in 3 hours in the west, in the north, and we're not actually going to skip part C because we can't do geometry in this class, but this is a trig-based class, you can do part C. So now we do the equation. What type of problem is this? This is a motion problem. Now we grab the equation, d equals vt, we have no acceleration, so we don't have to worry about that. And so we multiply this by 3, we get 105 miles. We multiply this by 3 and get 780 miles. And then we're done. If this was a trig-based class, for part C, the magnitude, you would take the north squared plus the west squared, but this is not, so we don't have to worry about that. But that's what it is for two-dimensions. We just now have 2 separate problems. We have to make sure the west is going to the west, the north is going to the north, or if we have a problem that's horizontal versus vertical, all the verticals are separated, all the horizontals are separated, and they're treated as 2 completely separate problems. This will be very important later on when we do projectiles. All right, so how do we change a velocity? Well, we learned in the first class, not on videotape, that to change a velocity we had to have an outside force. And what this outside force provides is something called an acceleration. Velocity is your rate of change of position. In other words, your rate of change or your change of position is called your distance. Your rate of change of velocity, if you change your velocity, is called acceleration. So at this point in time, I have to tell you about this funny looking triangle. It's called a delta. It's a Greek letter delta. We use this in physics to represent change. So delta means change. And change means final minus initial. Now it's important you do final minus initial. Not the biggest minus the smallest. Final minus initial. Sometimes your change is negative. So if you're slowing down, your delta, your change will be negative. Your change in velocity will be negative. Your acceleration in the direction you're moving will be negative. So distance is your delta x, your change in position, your final position minus your initial position. Your change in velocity equals acceleration times time. This A is acceleration, T is for time. And I always write capital T because if I write a lowercase t, it looks like a plus sign. So there's no particular reason for the capital T's. It's just my poor penmanship. So delta V equals acceleration times time. It's a delta V is final minus initial. My final velocity, now this is a little subscript, so I know what it is. I write a little f minus V initial, or you can write V not like I wrote up here. They both work. You can write any subscript you want, just as long as it makes sense to you and it'll make sense to me. Equals acceleration times time. Make sure that you realize that this is only the change in velocity. So if I have a question where I ask you for a final velocity and give you the acceleration of the time, don't just treat it as a level 1 problem. We go acceleration times time. 5 times 4 equals 20. That's my answer is 20. Well, not so much because that's your change in velocity. So in order to get the final velocity, you have to include the initial velocity. So that would almost be a level 2 problem. Alright, so if I solve this for acceleration instead of velocity, acceleration equals change in velocity divided by time. And on the exams, when I do the equation sheet, I will usually write this equation in a couple different ways to solve for the different variables, so you're not doing a lot of algebra on the exam. You're focused more on these two steps. What's happening in the problem, what problem types are these, and solve them. All right, and I can also break this down. Since final velocity equals initial minus initial velocity equals acceleration times time, I can move this over here and get that the final velocity equals the initial velocity plus acceleration times time. Now, I use the lowercase t in the PowerPoint because usually it's written as lowercase t. I write it as uppercase here, again, because I don't want you to confuse it with the plus sign. My handwriting is that bad. So let's do a quick example of this type of problem. So we have a car that's going to accelerate for 4 seconds and at 3 meters per second squared forward. By the way, all acceleration velocities have direction. I didn't write it here, but they always have direction. Always, always, always. And that's very important, especially if your direction changes. I give you the velocity 4 seconds later. Find the acceleration, and at this point in time, you may want to pause so that you can calculate this out. This is a level kind of, well, this is kind of a level 2 problem, maybe a level 1.5. Make sure you can solve this, and then once you've solved it, restart it up and watch me solve it as well. Again, solve it yourself. Watching me solve it will not help you solve it yourself later. It really doesn't. I know it's quicker, but it doesn't help. All right, step 1. What's happening to the problem? I have a car that's speeding up. What type of problem is this? This is a motion problem. Now grab the equation. The equation I'm going to use is this one right here. I'm only going to need one equation because this is not a level 3 problem. So my final velocity minus my initial velocity equals acceleration times time. My final velocity is 23 meters per second forward. And I'm going to write a little f to designate forward so I don't give myself carpal tunnel. You're welcome to do that as well. Minus the initial equals 3 meters per second squared, which means that every second I'm going to change my velocity, which is in meters per second, by 3 meters per second, times 4 seconds. And by the way, this is forward as well, even though I didn't specify it there. And now I just solve for my unknown. So I move this over and that over there. So I do this one step at a time, just because if I don't, I will confuse all of you. So I'm going to move VI over there. And multiply that out. Meters per second squared times a second is a meter per second. By the way, units, if done correctly, are your best friend. They take a few extra seconds to do, but it's worth it. If done incorrectly, we'll stab you in the back repeatedly. And now I solve for VI. So I subtract 12 from each side, and VI equals 11 meters per second forward. So if you think about it, this should make sense. If I start off at 11 meters per second, and I speed up 3 meters per second every second for 4 seconds, that's going to be 12 meters per second and I speed up. So my acceleration times time is 12 meters per second. That's how much I sped up. That was my change in velocity. So that means my final velocity is going to be my initial velocity plus my change, which is 12. So 11 plus 12 is 23, which is the final. That gives us what we call a sanity check to make sure our answer makes sense. Sometimes you do a sanity check and the answer doesn't make sense. You probably made a math error somewhere, or a sign error, or you left off direction, or you inverted something, etc. Lots of things that can go wrong. All right. At this point, I would ask for questions, but since there are none of you in the room except for me, I'm going to move on to the next slide. So another sample problem. I usually try to throw about 6 of these into each lecture, which before I post these online, I was only able to get to 2 or 3 of them, but now since it doesn't matter, I'm not constrained by the 15-minute time limit, I can spend more time on this. Hooray. Not too much time, though, so I won't sap all of your time. So now we have a runaway truck that is trying to slow down. Well, actually, they want to slow down, but first they're going down the hill. The brakes go away. So we're going to try to find the velocity after 10 seconds. And then after that, we're going to try to find, well, in the next slide, how long it'll take them to stop. So go ahead and do the top problem first. You may want to pause at this point. In fact, I can leave this up. Final velocity minus initial velocity equals acceleration at time. This is the exact same type of problem we had before, but we just changed the numbers a little bit. So in this case, instead of wanting to find the initial velocity, we're wanting to find the final velocity. And expect to be able to solve these equations for any variable. So I can have you solve for this one, or that one. They're all the same problem. I'm just having you solve for something slightly different. I know they seem like very different problems, but they are, in fact, the same problem. All right. But the numbers are changed to protect the innocent. Back with you. So my initial was 30. And I'm going to add this to this side to start. So VF equals V initial plus AT. So I'm going to do it like this.